The goal of this experiment is to use principles of blackbody radiation as well as spectrometry to determine the light color of various LED bulbs. Light color is a measurement of temperature described by how hot an idealized blackbody would need to be to produce the same spectrum produced by the light bulb. In this experiment, we will be using LED bulbs with light colors 2700 Kelvin, 3000 Kelvin, and 5000 Kelvin. To accomplish this, we designed a spectrometer through 3D printing that utilizes an iPhone 8. Next, we will apply Planck's law to determine whether or not the advertised light colors of various LED light bulbs is the same as the measured light colors. A black body is a theoretical object that absorbs 100% of the radiation that hits it. It reflects no radiation, hence the name blackbody. A couple examples of near-black bodies are stars and carbon in the form of granite, as most of the light directed at stars and carbon in the form of granite is absorbed, therefore making it capable of absorbing most wavelengths of electromagnetic radiation. Light bulbs are considered gray bodies since they do not absorb all the light and instead reflect part of the light incident on it. There are 3 different laws used to describe blackbody radiation. These 3 laws are Wien's displacement law, Rayleigh-Jean's law, and Planck's law. For the purpose of this experiment, we focus on Planck's law because it is universal for all wavelengths, whereas Wien's law is specific to smaller wavelengths and Rayleigh-Jean's is more accurate for larger wavelengths. Through Planck's law, we are able to determine the light color of LED lights by measuring the spectral radiance and wavelength and applying it to the equation with the known values of Planck's constant, Boltzmann's constant, and the speed of light. A spectrometer is a device that uses a diffraction grating to split light into a spectrum. The spectrometer was designed using Thingiverse.com and 3D Builder and was printed on a Lulzbot Mini. The dimensions used were formatted for an Apple iPhone 8. The entire design included 3 components, 2 of which utilized the 3D printer. The 3 components included the phone case, the spectrometer, and the diffraction grating. The phone case and the spectrometer were printed and then attached to each other by duct tape. When placed on the phone, the hole in the spectrometer aligns perfectly with the camera on the phone. Here is the finished product. Note that the spectrometer is attached to the phone case at a 45-degree angle. To complete the experiment, the spectrometer was assembled and calibrated. The calibrated spectrometer was then brought to the local Home Depot and used to capture the spectra of LED light bulbs with advertised light colors of 2700 Kelvin, 3000 Kelvin, and 5000 Kelvin. To eliminate ambient light, the spectrometer and bulb were covered with a piece of black cardstock paper. Each spectrum was captured 5 times. This process was repeated for all 3 light bulbs. Calibration of the spectrometer was done through the website Spectral Workbench. Using a compact fluorescent light bulb, the spectrometer was pointed at the bulb so that the spectrum was shown on the camera. The compact fluorescent light image was saved and a button marked Calibrate appeared. Upon clicking this button, the program attempted to auto-calibrate by automatically lining up the spectrum in the image previously captured with a reference spectrum. The reference spectrum was not correctly aligned with the captured spectrum through the auto-calibrate, so the sliders were dragged until the peaks in the 2 spectra were lined up. Each spectrum found in the experiment was then calibrated using Spectral Workbench. The reference spectrum for these images was the calibrated compact fluorescent light bulb spectrum done before. Through this calibration, the wavelength and the pixel intensity percentage were calculated. Pixel intensity percentage is later converted to normalized intensity, which is directly correlated to the normalized spectral radiance. Because of this direct correlation, the normalized intensity can be applied to the model described by Planck's law. Python was used to analyze the data and to determine whether or not the measured light colors matched that of the advertised. The data was plotted as measured wavelength versus measured spectral radiance. Error bars were used to account for the uncertainty. Planck's law was used to model a curve-fit function for each LED. From this analysis, we were able to determine the measured light color. For the 2700 Kelvin LED, the calculated light color was found to be 3373 Kelvin. This yielded a percent error of 24.3%. For the 3000 Kelvin LED, the light color was found to be 3940 Kelvin. This yielded a percent error of 31.33%. For the 5000 Kelvin LED, the light color was found to be 5902 Kelvin. This yielded a percent error of 12.04%. Based on the analysis of the data, it is clear that there must be misleading information somewhere in the experiment. This could be from sources of error such as ambient light, whether it be from surrounding light in the store or gaps where the spectrometer is connected to the phone case. The size of the light reduction slit could also be too large, resulting in overexposed images from the spectrometer. While it does seem that Spectral Workbench is a trusted open source, it could be that their calibration tool might have introduced errors that propagated through to the final calculation. Interestingly enough, the first 2 models had lower reduced chi-squared values but larger percent errors for light color, while the last model had the largest reduced chi-squared value but the smallest percent error for light color. Given these results, we must also consider the possibility of misleading or wrongful advertising by retailers. To improve this experiment, it would be beneficial to buy LED lights from Home Depot and do the experiment in a dark room to reduce the effects of ambient light, as well as construct a higher grade spectrometer.